Welcome to the Explainer. Today, we're diving into something that sounds simple, but is actually, well, it's a huge deal. How do we even map our planet's natural world? It's a story about how the very words we choose can completely change our predictions for the future. So let's just jump right in with a pretty provocative question, one that's right at the heart of climate science today. What if the very maps we rely on to understand nature aren't just a little off? What if they're fundamentally disagreeing with each other? And this isn't a small thing. A study back in 2008 found that two of the most common global vegetation maps out there, well, they disagree on how to classify about a third of the Earth's land. 1/3. That's not a rounding error. That is a massive, massive gap.
And look, this isn't just some nerdy debate for map makers. It's a huge problem, because the climate models we all count on to forecast what's coming, they use these maps as their starting point. So if the maps don't even agree, how can we trust the predictions?
Okay, so to really get our heads around why this is happening, we've got to take a step back. We need to understand the basic building blocks of these maps. What are we even trying to put a label on in the first place?
So the word is biome. And really, you can just think of it as a major category of nature. It's a huge community of plants and animals that all share a similar climate. A tropical rainforest, that's a biome. A desert, that's a biome too. These are the big puzzle pieces for our global maps.
But here's the thing. How we define these puzzle pieces has totally changed over the years. Way back over a century ago, we just looked at what kinds of plants were around. Then we started sorting things by climate zones. And today we're using super high-res satellite data, which gives us this incredibly detailed picture. It just keeps getting more complex.
And this really gets to the core of the challenge. Think about organizing your music, right? How do you do it? Do you sort by genre, by artist, maybe by the decade it came out? Now, none of those ways is wrong, but each one gives you a completely different looking library. It's the exact same thing with nature. Do you map by plant type or by climate? Each choice creates a totally different map of the world.
So this whole problem is pushing scientists to find a new way to see the plant world, one that's a little more flexible and nuanced, especially when they're trying to build these really important climate models.
So the old way, that's what we call plant functional types, or PFTs. This is like just lumping your music into rock or pop. It's useful, sure, but it's super broad. The new way gets way more specific. It focuses on what are called plant traits. These are things you can actually measure, like how big a plant's leaves are, how dense its wood is, or how tall it gets. It's like looking at the song's actual tempo and key, much more detail.
And when scientists really started digging into this data, they found something pretty cool. A recent study found that just a few key traits were way more important than others for telling biomes apart. And what were they? Well, it turns out they're all about a plant's size and structure, its crown area, the diameter of its stem, its height, and its age.
Okay, so we've got the old way with its broad categories, and this new way with its super specific traits. But why does this switch matter so much? Why is it so critical for figuring out our future? Well, the answer changes everything.
This quote from the research just nails it. The method you pick to classify nature doesn't just change how the map looks today, it fundamentally changes the prediction for tomorrow. It directly impacts which parts of the world we think are most at risk.
And here is the absolute kicker. When scientists ran their climate models using these different mapping methods, the results were just wildly different. Depending on which map they started with, their projection for how much of the world's natural land will go through a major change this century went from about 16.5% all the way up to over 32%. That is literally double the predicted risk.
Let's be really clear about this. That huge gap isn't because of different climate data. Nope, they use the exact same climate scenarios for both. The entire difference comes down to how we choose to label the natural world. Our definitions are, in a very real way, shaping our predictions about the future.
But okay, it's not all just uncertainty and confusion. Actually, when you step back and you look at all these different maps together, a really powerful and consistent signal starts to emerge. And this is where things get interesting.
And this is so important. No matter which classification method the scientists used, it didn't matter if it was the old one or the new one, the same kinds of ecosystems kept showing up as either the most vulnerable to change or the most stable. And here's that consensus. Across all the different models, all the different maps, grasslands and savannas are consistently flagged as the ecosystems that are most likely to change. And on the flip side, tropical forests and deserts are projected to be the most stable.
So even if the details are a little fuzzy, the big picture is starting to get really sharp.
So what's the big takeaway here? The labels we use for nature are still a work in progress, and they really do shape how we see the future. But even with that uncertainty, the collective warning from all these different maps is crystal clear. It points to specific areas of risk and specific areas of resilience. Which leaves us with the final and most important question: how are we going to respond?